Monday and Wednesday. So right after this class, which is nice. You guys can just stay in the calculus zone and come right on by. Yeah, I mean, we're gonna mostly just work on study skills and a continuation of what you guys do in class. So if you feel like you need the extra help and want to come through, please do. We're just gonna make sure everyone understands everything as much as possible. So yeah, today it's gonna be in room 9253. It's in the STEM Center. I'm sure most of you have seen it. Yeah, please come on by.
And what did you guys say something about the book? Like, was it helpful? Don't say if it happened. Yeah.
So yeah, last semester we were taking ethics for physics and it was very helpful, especially for the midterms, or in case you didn't understand something or you have some questions. Especially because if you have some question and you don't have time to like ask your professor or something, the ethics tutors will help you with that. They really help. Really help.
When you go to an epic, you meet people that are struggling like you, so you're able to form a study group because of that. So if you can't make it on Monday or Wednesday because you already know the people in the epic, you can study Tuesday or Thursday.
All right.
I also the way I was participating in this 2, 1, and 2.5. So yeah, what happens is that imagine going to an exam and you just kind of get things a little bit when there's an epic, they just kind of bring it up, even if you think you're prepared for what's coming up.
Okay. All right. Good plugs. Thank you. And anything else you want to say, Mo?
I just hope everyone comes by. I think we're gonna try to get a good group together and just make sure everyone's as prepared as possible for everything.
All
right.
Thank you.
Other announcements I found in my email, there's some Career Center. The spring internship fair happens on February 5th at the Grove. It's 11 to 1, so you can try to make it there before class. And there's a job fair also from 11 to 1, 1:30-ish, but that's not till April. And then anybody who wants to study Spanish, interested in going abroad to Spain to study Spanish, Spain, Spanish, as opposed to like Puerto Rican Spanish, which is what I went to Puerto Rico this past winter break, and it's kind of different from Mexican Spanish. So the Spanish is probably different from the California Spanish that we have, but it's all about learning about cultures and stuff. So Thursday, January 30th, 1 to 2, that's during our class time. So ask her to come by here either today or tomorrow. And if she doesn't, I'll send her an email if anybody's interested, because this kind of goes during our class time to see if you can get some information. All right, so if anybody's interested, let me know, or you can look her up, Mahmoud. Anything else? All right, any clubs starting this week, for the semester? Anybody involved with clubs? I know our speaker series is going to start sometime in February. Okay. All right, so today our focus will be on 12.1, Introduction to 3D Space. Right? See if I have it here. No, I didn't make it public yet. Oh yeah. Is it in the syllabus? So one point.
But it's only on like 7.
Yeah, 1 point for the final exam, each attendance over there. And then, but you can, so I think they have 7 of them, so you can only go up to 5 points. Yeah. For the what?
If we get rated to the STEM series and they post it online, we just watch that instead.
Yeah. So there's an option to watch the videos too, and that you need to sign up for the STEM Speaker Series Canvas site. And I'm not exactly sure how that goes, but if you have any questions, Rance is at the STEM Center, and he can answer those questions. Alexi? If you attend and go there and sign up and then put my name as part of the extra credit, then you don't have to write anything up. But if you watch it or do something different, then you have to do a little, just a small paragraph. But yeah, actually go there. Yeah, yeah, there's food. So I didn't have time to write a script on this. I was going to say space, final frontier for calculus 3 and stuff like that. Maybe for next semester. So we are going to deal with 3-dimensional space. Everything that we've done, everything that you've done so far from pre-calculus, calculus 1, calculus 2 has been looking at just 2-dimensional space, graphs and things like that. So now we're going to take a look at what happens in 3D. And since we can view things in 3 dimensions, and that's what we're going to be able to study. Of course, we can't see it when we're looking at a flat screen, but we can try to imagine what it might look like by looking at 3-dimensional graphs and trying to draw in 3 dimensions, etc. When we deal with the vectors, or the next things that we're going to talk about in the next section, when we do that, vectors can exist not just in 2 or 3 dimensions, but can also exist in 4, 5, 6 dimensions, as many dimensions as you want. And so, unfortunately, we can't visualize those anymore, unless you're on some stuff that helps you see things. But we might be able to see some representations. 4 dimensions, we might be able to see some representations as a carryover from our step from 2D to 3D. We might be able to pretend that something exists in 4 dimensions. I mean, they exist, but you just can't see them. So we can pretend to visualize them as we go from 3D to 4D. And then beyond that, it's just kind of crazy. But they still do exist mathematically. Anything like that can exist abstractly, and we'll still be able to process ideas and things about it. So space, that's what we're going to do. All right, so in 3-dimensional space, we're going to introduce a new, did you guys get my announcement, by the way? There's some Zoom stuff that was happening, and so I'm testing out this new way to try to record things. We'll see if it works. If it doesn't, then you don't have a recording for this class. Zoom? Oh, for Zoom? Okay. And I think I'm recording it. That's what this dot is, right? Yeah, but I'm always talking. I mean, I'm talking here, but I think, yeah, I think that's what this dot is. Yeah. Well, I hope so. Like I said, if it doesn't happen, I apologize. We're not going to have a video for this class, but the last 4 times I did this. Okay. Let's get going with 3D space. So in 3-dimensional space, we have X and Y in 2D that we've seen before. Well, let's start off with 1 dimension. I still have my orange pen. I don't know if you guys remember our first day drawing. We were drawing the the parametric equations, and I had somebody deal with the t-axis. I think that was Kalea. He was dealing with the t-axis, and the t-axis can represent a one-dimensional axis. And in one dimension, you can go forward and backwards, but that's about it. And then so we give ourselves some room to go 2 dimensions, where we go along an x value or along an x-axis and along a y-axis. And now we're spreading, instead of going forwards and backwards, we can go forwards, backwards, and up and down. And so now we have 2 directions in which to go by. And that's what we've studied. And then with this x and y variable, we can define graphs or relationships between x and y. Relationships between x and y, like you know, like a line, y is equal to x, like a circle, x squared plus y squared is equal to 1, like any other graphs that we might have seen in pre-calculus, or any of those conic section graphs that we've seen just last week. We can see the relationship between them by a graph, because the equality, the equal sign, kind of controls the x and the y values together. So if x was something, then y is something, and then we would plot those coordinate points. So now we're looking at going to 3 dimensions, and for that, we want to be able to represent them in a drawing. And so as an extension, we're just going to look at 2 dimensions, and then we're going to add a 3rd axis to it. And so in our 3-dimensional representation of this, you probably have seen this, and if you haven't, welcome to space. We're going to have an x and y, just like we had in 2 dimensions, and then we're going to have a z. And we're going to draw this with perspective. So the perspective is that this x-axis, we can imagine, if you drew it this way, you can imagine the x-axis is coming straight at you out of the screen. So now there's forward and backwards along the x-axis. We have the left and right in the y-axis. And then we throw a 3rd direction over there in what we'll call a z-axis that goes up and down. So drawing this is half the battle of visualizing it, because what we want to do is when we draw these things, we kind of want it to make sense with our eyes and make it match up with the perspective that we're drawing. And so drawing the axis is the first step. After you draw the axis, imagine the grid that you would draw for the 2-dimensional graph. And by grid, I mean the Cartesian grid, because now we talked about polar coordinate grids, right? So now let's go back to the idea of a Cartesian grid or a rectangular grid, and then you would have rectangles. Now, if you were to draw this on the x and y axis, or the x and y, I guess we can call it a plane now, a whole x and y plane, I would draw lines parallel to both the x and the y. So drawing a line parallel to the y-axis, since it's going horizontal, seems like it makes sense. But when you draw a line parallel to the x, you have to draw it parallel to the x. So all those lines that are going to be going along the x would be parallel to the x-axis. And I think and then if you try to do it this way, you can kind of see it looks like that 2-dimensional grid that we drew in 2 dimensions, except now it's flat on the ground, where x is coming at you and y is going to the right, a positive y is going to the right. So if you want negative x, you go back behind the screen. And then if you want the negative y, you go to the left side of y. And then this is what you have. Okay. And so what we would do is we would acknowledge different points on this 3-dimensional grid that we're trying to draw. And the same way where we march along the X and march along the Y to plot points in the XY space or XY plane, we can also do the same thing here. We can march along the X. Let's say we have an X value. Say we have an X value of 1, a Y value of 2, and then a Z value of 3. You would imagine a grid, or actually draw it out, where you would go 1 unit along the Y coordinate, and then 2 units. Now the 2 units in the 1 unit in the X coordinate, the 2 units in the Y coordinate would be parallel to the Y axis. So on the Y axis, you would mark it on the Y axis, but then you would actually draw it here. So if we stop and pause there and not look at the third one yet, we can kind of see the box that we would normally draw. And it's a rectangle. It looks like a parallelogram because we're seeing it at an angle, but it's really just a rectangle. That's the point 1, 2. Except we're looking at it flat, so that's what we're seeing. And then from there, we're going to go up 3 units, and by up, I mean up along the z-axis, 1, 2, 3. Now, this is the axis that we're moving up on, but what would be really nice to do is that if you draw that axis, or you draw that length on the z-axis, what you want to do is you want to take that length in the z-axis and move it to where you left off in the y-axis. I know you can't do that on your paper, so you just kind of have to measure, you kind of just have to measure your z-axis steps and then draw that same length up where you are. And so when you do this, you end up with a point 1, 2, 3. Not only do you end up with a point, but you can also draw. You don't have to do this, but you can also complete a box, a cube. It's not a perfect cube because the side lengths are all different, but you would be able to draw a box that would contain that point in the corner and then the origin at the other corner. Okay. All right. So if we go back to the two-dimensional drawing that we have the X and the Y axes kind of separating the whole plane into 4 pieces, and so we called it quadrants. And then as we're calling it quadrants, we designated names for them or numbers for them. And the general rule is the first quadrant would be the one where both the X and the Y are positive. And then the last quadrant is where, well, the third quadrant's when they're both negative. And then the second and fourth quadrant are when one of them's negative, one's positive. So now if you imagine cutting your space up with these axes, you essentially have how many spaces? 4, 6, 8. So there would be 8 octants. Now the most important octant is probably the first octant. And just like the first quadrant is when all the variables are positive. So the first octant is the octant that we're going to be referring to the most. After that, we can just imagine the quadrants when Z is positive and when Z is negative. So the second, third, and fourth octants would be all when Z is equal to 0. And then we would just follow the rules for the x and y for the octants themselves. So the second octant, I think when x is negative and y is positive. The third octant are when both are negative. And the fourth octant is when x is positive, y is still negative. So if we follow, copy and paste that onto where z is negative, we can have the fifth, sixth, the seventh, and the eighth. You guys know your Roman numerals? So these things will happen below the xy plane. And then we'll say x and y are both positive. The third octant when they're both negative. And then this is when they switch. So x is negative, y is positive. X is positive, y is negative. So those are the octants that would occupy your whole space in 3 dimensions. Space, final frontier. Okay, yes. An octant is a 1/8 of the space that we're looking at that's divided by the x, y, and z axes. No, planes. It has to be divided by the planes. And so we need to talk about the planes like really soon. Just like a quadrant back in 2 dimensions. A quadrant is when the axis splits up your plane, your 2-dimensional plane into 4 spaces. An octant will split up your space into 8 spaces. Yeah. Except that z is positive in the 4th octant and z is negative in the 8th octant. Yeah. So the first 4 octants can be just like the 2-dimensional quadrants when z is positive, and then the last 4 octants is like the 2-dimensional quadrants except when z is negative. All right, let's talk about the coordinate planes. So I guess to really first start talking about this octant, which is probably, I should have started with this first. The idea is that space is going to be broken up to 8 spaces. And so the first space that we could look at is this. The first plane that let's look at is the XY plane. So the XY plane are all values when z is equal to 0. So when z is equal to 0, you have this XY plane that cuts your space in half. Okay, and then above it would be z is positive, below it would be z is negative. And now there's 2 other coordinate planes that we can look at, the YZ plane. And the YZ plane is when the other variable, right, if you see the relationship here already, the other variable is equal to 0. And then the ZX plane or XZ plane is when Y is equal to 0. Okay, so that's where we're moving towards. We're moving towards describing things in space using equations. So between these 3 equations, z is equal to 0, x is equal to 0, and y is equal to 0, now we have 3 planes that intersect each other, and that would divide this space into 8 spaces that we're going to call octants. So since these are the dividers, it's when things are positive and negative that actually let us know which octant we're in. Okay. Can you guys see this? Well, fortunately, we have a very cool tool that helps us see this. No. Oh, I can't. Yeah, this is better. Calc plot 3D. So if you Google Calc plot 3D, Monroe Community College had a grant where they developed this visualizing tool. This is the default generic function that they put in here, and functions of more than one variable is something we'll take a look at in chapter 14. And so let's hide that for now. And right now what we're doing are really, they're called implicit surfaces. And z is equal to 0 is our first implicit surface that we're going to look at. Surface, and that is just the XY plane. There's this box, default box, that I really don't like, and so I always have to take a minute to get rid of that. But yeah, you can take this drawing and move it around and spin it and do all kinds of crazy stuff with it. All right, so that's one plane. So if you imagine what y is equal to 0 is going to look like, what do you think it's going to look like? Well, it's going to be a plane. Vertical. Oh, it's vertical, but it has to pass through what? X-axis and Z-axis. So passing through the X-axis and the Z-axis is your plane. And then our last one, we include another implicit surface here. Look at all these surfaces that they have. Let's just take a look at this. This is 9x squared plus y squared minus 9z squared minus 40x. Hey, that kind of looks familiar, huh? It looks like it might be. What? Egg-shaped? Good. Good. Could be. Oh, no, no, no. Does it want to make you pull up your computer now and mess around with this? That's the idea. I mean, you can watch me do this all day, but unless you actually try it, you're not going to get a taste of it, especially since it might be useful for your test, right? Oh, you can see the octants, huh? So another neat thing about this is that you can make it transparent. So in case I'm trying to hide a point from you. So we got that point 1, 2, 3. I don't think the 1, 2, 3 is going to fit here since our limits only go up to 2. But if I throw a point in here, just say 1, 1, 1. You can see it pop up over here, right, in the first octant. Let's play a game called Which Octant? 1, -1, +1. Which octant? Okay, one of the first 4. The answer on your test. 1, Put it on your test. 1, 2, 3, 4. It'll be like a clicker question. Just maybe I'll stand here. All right. The answer. All right, I got a bunch of 4s and 2s. 4 is when x is positive, y is negative, and z is positive. So is it in 4th quadrant? There'll be 1, 2, 3. There it goes. It is, huh? Not. What if I put a negative there? Which octant is this going to be in? I guess you can't do it one. Okay, sign language. 1, 2, 3, 4, 5, 6, 7, 8, 6. Oh, this is 7. This is 6. This is 7. Six, 7, 8. 8 is the middle finger. 6. That's 7. what's yeah. And then this is 10. All right, so a lot of 8s. A lot of 8s. The 8th would be, oops, would be down here somewhere. There he goes. What? Oh, then you would say it's on the axis somewhere. Like, give me a point on the y-axis. No, but what would be as a 3-dimensional point? 0, 1, 0. 0, 1, 0. Uh-oh, there you go. There he goes. Let's make it larger. Let's make it red. You can also, I started to do this, but I thought I'd play that hide the point game from you. It's a fun game. Play it with my kids all the time. So now it's transparent, so you can see. You can also hide the wires. All right, so this is a pretty fun program that you can mess around with. It's free. The only thing is Desmos, if you sign in, you can save your work. Here, you can't save your work. I mean, you could take a picture of all the stuff you've inputted, but if you're trying to build up to try to create something, which is what I'll be doing in class, is trying to show you stuff, we won't be able to keep it. So to recreate it, I could just take a picture of all the stuff on the side. Yeah. No, I tried. GeoGebra has a 3D visualization. And so, in fact, I have a 3D visualization graph. With what?
The equation. I want to see that.
So those equations are like preset. So if you comment on the equation,
There'll be another preset, yeah.
yeah. So eventually it's someone else.
Let's see if we can draw. So Here, David, hold your hand up like this. Uh-oh, where is it? I'm just messing around with this. This is really not of any consequence for anything. Should I do this? Yes. All right, somebody can tell me.
9, 8, 7, 6, 5, 4, 3, 2, 1.
All right. Maybe I'll show it to you tomorrow. I can't get to it, and then it's just wasting time. So, I have an AR. I have GeoGebra with AR, so I could draw a graph, take a picture of something, and then that graph will be there. So it was supposed to be, you're supposed to be holding it, but it's actually covering you, so you can't even see you. Oh, you're still on my phone, so I'll show it in class tomorrow. All right. So the idea is that you have these coordinate planes. You have the X, Y, Z axis now to visualize. We could draw little bits of it. And when we run into an object that we have to try to draw, I'll try to draw it by hand first before relying on this, because I don't want you to fully just rely on this. I want you to be able to draw a little bit of it, and then use your imagination, and then finally use this technology to confirm what it is that you're trying to imagine or trying to see.
Are we responsible to solve complex planes and stuff like that?
Yeah, I would expect you to be able to do that. I don't know how much of the drawing, but definitely be able to visualize it using this. And then so part of that might be for you to try to draw it yourselves, or for you to try to explain it in words. All right, so we have the general idea. Let's take a look at more equations. We have the coordinate planes as our first set of equations. But now let's take a look at some other equations. I don't know, maybe I should take a look at my notes, see what I said in my notes. Somebody do a countdown again. Never mind, I already got it. I was going to say 10. Visualize, coordinate plane. Oh, okay, so let's take a look at planes, more planes parallel to the y-axis and z-axis and x-axis, or parallel to the xy plane, the yz plane, and xz plane. So when we have in 2 dimensions, when we have the xy plane, and then we say x equals 5, that would be a line parallel to the y-axis, right? And when we say, in 2 dimensions also, when we say y is equal to -1, that would be a horizontal line parallel to the x-axis. So we could also take a look at parallel planes, like when we say z is equal to a bunch of numbers different from 0. So aside from z is equal to 0, when z is equal to a constant, then this would just be a plane that's parallel to the z is equal to 0 plane, which is parallel to the xy plane. So these are all parallel to the xy plane. And then again, I would encourage you to try to draw these things. And for planes, technically, if you draw a plane, they go on forever. But you know, just like you would draw a line, you would just eventually stop and just imagine it would go on forever. But to try to draw a plane, I would draw where it would intersect one of the axes that we're talking about. And then again, draw a rectangular region. And when you're drawing a rectangular region with perspective, you have to draw it parallel to the axis that it's supposed to be parallel to. So these are all parallel to the XY axes, the x-axis and the y-axis. And so I'll kind of draw it like this and say that intersects the z-axis at 1. And then draw another plane up on top of that. Where you would have that plane intersect the z-axis at 2. And then down below, you can draw the other z-axis, or z equals -1 plane, parallel to the xy plane again. It's intersecting the z-axis at z is equal to -1.
What happens if you have geometry like forever and ever again, we were drawing a line up to infinity, they always had us indicate a capital little arrow.
Yeah.
Is there an equivalent here?
No,
Okay.
no, we can't. Yeah, you can't just draw an arrow and say it goes on forever, but we can just say, here, it looks like this and it goes on forever. But this is a piece that we're seeing. What do you think?
I don't know if we know what happens. Like we say x plus y, is that a thing?
Yeah, that's probably going to be a plane. That's probably going to be a slope plane. Well, we'll take a look at those equations momentarily. So you could imagine that if you have y is equal to 5, then that's a line parallel, or that's a plane parallel to the xz axis. So y equals k parallel to, you can think about it as parallel to y is equal to 0, which is really the xz plane or zx plane. Xz, zx, they're the same thing, except people tend to like to use zx plane better because of the right-hand rule. We'll talk about later. If you've had physics before, you should have some idea of what that right-hand rule is. All right, and then the last one is when x is equal to a bunch of constants, that's parallel to the x equals 0 plane, which is the yz plane. And we can see pictures of that in, I mean, we can imagine how this would look like, right? You don't need much imagination for this, but here we can define a slider. A is equal to 1, and then we can have a point or have another implicit surface let's say z is equal to a, when a equals 1, and then can move it and animate it. Cool, huh? And then when it's x equals to a, x equals to a is parallel to the what coordinate plane? YZ. The YZ plane. Okay. All right. Now let's take a look at did somebody say, what is it? X plus y equals 1? All right, let's take a look at this. And there's also one I wanted to take a look at. That's the x plus y squared is equal to 1. What is x squared plus y squared is equal to 1? Circle, right? Okay, so let's hold that off in a minute. Let's see. If I were to draw this in 2 dimensions, because it has x and y, does it make you want to draw in 2 dimensions? Yeah. What does this look like? Negative sloping line. Oh. That's this line, right? But now we want to imagine this thing in 3 dimensions. So what do we want to do? What we want to do is we want to imagine this thing flat on the XY plane. And again, so now this is where you have to use your perspective. So I'm going to try to draw, since when I draw it in 2 dimensions, I draw the positive and negative axis. So I'm going to imagine the negative x going down here and the negative y going down here. Now I'm going to attempt to draw this. This is happening in the 2nd and 3rd quadrant, right? So this is the 1st quadrant right here. This is the 2nd quadrant. So it's happening and cutting the 2nd quadrant kind of like in half, and then cutting this in half as well. So this line here actually exists in 2 dimensions from a 3D perspective where it is right now. So now to imagine this in 3 dimensions, you would just make this line get swept up and down the z-axis. So the z is not, I don't see a z here, right? So what that means is that if you don't see one of the variables there, you can draw this as a 2-dimensional graph and the 2 variable axis that they exist in, and then you can sweep it up the 3rd missing variable axis. So I would make it go up along the z, down along the z. So it would be that plane. This is where it gets a little bit tough to look at because I can't take a look at my picture and twist it around and stuff. So this is where you could try to visualize it like this, but let's take a look at it in 3D cop plotter. Where is it? Oh, here it goes. So let's get rid of that slider for now. What was that equation? X plus y equals 0. That's pretty much what I drew. No, seriously, it is. I mean, if you make it transparent. You still can't see it. But better if you put it sideways. Oh, you know what? Would be a better view. Look at it from the top. from the top. There he goes. So the x and y, as if we're looking at it two-dimensionally, and it's running across there. So that's the visual that we would see from the top. And essentially, if this was just projected on the xy plane, it would just be a line. Yeah.
Looking at 2D is just like not looking.
Yes. Back to the x squared plus y squared. If I were to ask you to graph x squared plus y squared in 3 dimensions, what would it look like? It's a cylinder. Right? So, yeah. Let's draw it by hand first, because by let's, I mean, you guys should try to draw it by hand also. And see if you could take the same approach where you would take a look at the two-dimensional graph first, and then a 3D graph. So remember, back in 2 dimensions, that would just be a circle. So now if you try to draw it in 3D, I would first attempt to draw that graph on the XY plane, and it would look kind of oblongish because it's flattened out and you're looking at it with perspective. And then you sweep it up and down. Okay, so again, if we take a look at it here, I think I have to grab the axis, no? There, it's just a cylinder. Okay. Parabola? This isn't a parabola. Oh, yeah, yeah. Yes. Let's see. Yep, nothing in the middle. So these are surfaces that we're looking at. So if it might look like a solid, it's really just the surface that we're looking at. Unless we use some sort of inequality, in which case I don't know if this could draw it. Nope, an error. So it has to be an equality and it has to be a surface. Okay. All right. So what I want you to do is try to draw. Wait, after I take a picture of this. Speaking of parabola, why don't you guys try to draw this? So there's a variable missing, right? And again, the practice is to try to draw this by hand, and then we'll take a look at how this looks like in the computer. What did you guys draw? Try to explain it in words. Yeah, Ty. Trough. That's exactly what I was thinking of. Trough. You guys have trough problems in gutters. Trough problems in your calc too, like pushing the water out. Remember that work? No. Wow. Fortunately, we don't have to do that in our class. So I would draw a line parallel to it's being swept along the x-axis. So I would draw a line parallel to the x-axis and try to mimic the same drawing to get that picture of a trough. Maybe we'll throw the edges back in here. Okay. Yeah. Like a one-dimensional line? Maybe in the next section. Or should I show you now? All right, well, I wanted to graph this anyways when we had the cylinder up. So I'll give you a little preview. So a line is essentially a curve. And then we know how to draw curves using just regular graphs, but we also learn how to draw curves using parametric equations, right? And so the way to draw lines in three-dimensional space would be the same as to draw curves in three-dimensional space, which is dealing with parametric equations. So a parametric equation, if you remember the sine and cosine, that was our very first example on the first day where people were drawing the circle, and it's cosine and sine, right? And so we have a third dimension here where if the third dimension is just equal to 0, then you're just flat on the xy plane. So if you let our t go from 0 to 2 pi, which we've done before, and draw this, this would be your curve in 2 dimensions. So try to think about what would happen if I wanted to just draw a line instead of a curve, and line in space going from one point to another. We'll get to that, like I said, a couple of sections from now. The default here, when you first ask for a space curve, is a cosine and sine, and then they have like a 0.1 t. What do you think this graph is going to look like? Your z, so your x and y are going around in a circle, like a spring, spiral. So to make this more dramatic, let's make it go from -10 to 10, like which is what they had. So as your x and y are going in circles, your z is going up or down if it goes negative. Okay, so we'll study that as well. Just like a preview. All right. Anyways, these graphs where one of the variables is missing, there's actually a special name for them. I don't have it here. It's called a cylinder. Well, you think a cylinder is that thing, right? But we're going to call different things cylinders. So maybe I should check this up. Described by two variables. So a cylinder, the cylinder that we know of would be called the circular cylinder. Which, by the way, we can also change the orientation, right? Say if we had y squared plus z squared equals 1. This is still going to be a circular cylinder, except which way is it going? Along the x-axis. Looks like a dance move. What is x squared minus y squared is equal to 1? What is that shape? It's a hyperbola. Why? You guys didn't forget that, did you? Remember our gang sign? We're in the Calc 3 gang. Like, you super geek, right? Yeah, what's up? We'll see that when we're looking at these shapes in 3 dimensions, there's going to be a noun. I'm going to go grammar on you again. A noun that describes the shape itself, and then an adjective that describes what that noun is. That's what adjectives do, right? And so this drawing that we just did over here, where we had y is equal to, or z is equal to y squared or whatever, where we saw that it was like a trough. There's this extra line here I don't like. So this is a cylinder because it's being swept, so that's my noun. But the adjective that describes it is, what is the shape in 2 dimensions? So it's a parabola, so we would say it's a parabolic cylinder. And we'll see this when we learn more shapes. The noun just says that it's a graph that's being swept along an axis, 2 variables. So this is a, how we should describe it, 2D graph of something. The equation, that's not even right, is being swept along the missing variable axis. Wow. Good thing I can move things around. No. No, those are just underlines. So when we hear cylinder, we can move away from the idea that it's all circles, right? Oh, there's one more. X squared plus y squared plus z squared is equal to 1. That's a sphere. So x squared plus y squared, and then the third one is equal to 1. So let me just graph that and put it on, and then it'll be in your notes because it's 151. There's a distance formula in 3D, and there's the equation of the sphere. So I'll just put that in the notes that you guys are all going to take a look at and download sometime anyways. All right, so space, final frontier.